And I think we can agree that it can get a little time consuming on some of these problems, and it requires some pretty good algebra skills. I mean, that's really what we were doing. Not necessarily calculus, but lots of algebra this past week. There are some shortcuts that can be used to find derivatives. So that's the next piece that we're going to talk about. We're going to start out trying to maybe prove what some of these things are, and then seeing if we can derive rules from there. So let's say you just have a constant. F of x equals some number. Okay, we know if we graph like y equals 4, it's just a horizontal line. What's the slope of a horizontal line? So if a derivative is the slope of the tangent line, what would be the derivative of this? Still 0, right? The tangent line is just the line itself in this case, and it would have a slope of 0. So what that means is the derivative of any constant is 0. We had that come up on one of the homework problems when it had you do like the fourth derivative. Your third derivative was 6, and your fourth derivative turned out to be 0. And so that's always the case. I want to prove some of these things. I really haven't proven a lot for you, and I just wanted to show you how some of those might work. The proof piece isn't necessarily something that I would ask you to do, but if you go on to take further math classes, you will see it, so I want to make sure that you've seen them before. If, let's say I just have a function f of x equals c. If we work through the derivative of this by our definition, limit h approaches 0, f of x plus h minus f of x all over h, you get the limit as h approaches 0. If f of x is just equal to a number, then what is f of x plus h? The same number, it's just c, right? Minus f of x is c over h. So I get 0 over h, or the limit h approaches 0 of 0, which is 0. So for any constant, you no longer have to go through the definition. If you see a constant, you can automatically say its derivative is equal. All right, so that is the first rule. So that's in the box there. You can highlight that if you want. That is now something you can assume moving forward. I want to go through a few of the power functions here. Please try not to look ahead to the rule. I want to see if we can figure out the rule on our own. So we're going to start with the very basic ones, x to a power. If it's just x to the first, y equals x, that's a line with a slope of 1. So its derivative should be 1. Okay? Then if it's x squared, we can't necessarily just look at the line anymore. So if we actually did the definition, so we're talking about if f of x equals x squared, then we have the limit h approaches 0, f of x plus h, so x plus h squared minus f of x all over h. So we multiply that out, we get x squared plus 2xh plus h squared minus x squared. X squareds drop. If you cancel an h out of everything, you have 2x plus h. Plug in a 0 for your h, and what do we get? 2x. So here's what we have so far. Okay, so if our derivative is just, or if our function is constant, the derivative is 0. If the function is x, the derivative is 1. If it's x squared, the derivative is 2x. Let's do x cubed. So we have x plus h cubed minus x cubed all over h. If I just write down what x plus h cubed is without actually showing you guys how I got that, is that okay? You guys know how to write it 3 times and FOIL it all out if you had to. So we would get x cubed plus 3x squared h plus 3xh squared plus h cubed minus that x cubed on the end. So the x cubes drop. If you cancel an h out of everything, you get 3x squared plus 3xh plus h squared. Plug in a 0 for all of your h's, and what do you get? 3x squared. So the derivative of x cubed is 3x squared. You seeing patterns yet? Maybe. I think we can do one last one, and this will probably be the last thing we do today, so we'll pick up with this stuff on Tuesday. For the 4th, we've got the limit as h approaches 0, f of x plus h minus f of x all over h. Okay, so I have to do this thing to the 4th power. I'm going to use that little triangle trick I showed you guys the other day. So this, so we're on this row. Those are your coefficients. So I have a 1x to the 4th, a 4x cubed h, a 6x squared h squared, 4x h cubed, and then h to the 4th. Do you guys see how I got that? Minus that x to the 4th we had on the end, all over h. So x is dropped. Canceling h out of everything, you have 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Plug in a 0 for your h's, and what do you get? So the derivative of x to the 4th is 4x cubed. If I put x to the 5th up here, what do you think it would be? Okay. So, if I said x to the 99th, do you guys see this pattern? What's happening is the exponent is coming down in front, and you subtract 1 from the power. So x cubed, 3 comes down in front, 3 minus 1 is 2. X to the 4th, 4 drops down in front, 4 minus 1 is 3. That works up here. This was an x to the 1st, so the 1 comes down. If you subtract 1 from the power, that's x to the 0. And x to the 0 is just 1. Okay. So that is our huge result. This is the power rule. You can now accept this as fact. From now on, if you have x to a power, you can do its derivative like this. So that means not even just nice pretty ones. If I said x to the negative 7/5 power, we could do its derivative. The exponent comes down. S, what's negative 7/5 minus 1? So if it's x to a power, we can automatically do its derivative without going through the whole definition. So that is the piece we will pick up with
on Tuesday.